Okay, this is a little run through on how to use Sage, especially for using matrices and so forth. What you do is you go to sagemath.org, sagemath.org, and especially at the beginning, I just recommend you do the online version right here. Use this button. It's possible to download it, but be warned, Sage, the native environment for Sage is Linux, and so if you have a Linux machine, it's not a big deal. If you have Windows or Mac, what you end up doing is downloading a virtual machine that will run Linux within your Windows or Mac environment. And that's an interesting thing to learn how to do. However, when you're trying to just learn how to use the matrix operators and so forth, that's sort of the long way around to get to actually doing what you set out to do. Okay, so let's click here. And the first thing that's going to happen is you have to log in. And I'm just going to use my Google login. And here I am. All right, this is me. And Intro to Matrices in Sage is what I'm running. Okay, this is my Sage notebook, Intro to Matrices in Sage. And I'm starting off just introducing what comments look like. I wanted to put text in here interleaved with my actual operations, okay? So everything with a hash mark out in the front is a comment. And if you put 3 quotes, you can put multi-line comments in here. This gives me a chance to describe what I'm doing apart from doing it. So just to get to know Sage a little bit, I've started off with just sort of putting in pi. If you type in pi and then you hit evaluate, it comes up with pi. This is sort of like saying print. So if I say print pi, it's the same thing, except the only time you can just say pi and it'll print as if it's the only thing there. So print pi is a more general way to say it. And guess what? It prints pi. Now, what if I want the digits of pi? Pi, which is a symbol, which is a constant actually embedded in Sage, has a numeric version. And so if I say pi.n parentheses, parentheses, this is the notation in Python, which is the programming language that lays behind Sage. And if I say pi.n, this is going to invoke give me the numerical version kind of an operation. Okay, so if I hit evaluate, there it is. It gives me a default number of digits of pi, quite a few actually. All right, but what if I put print pi.n 100? What it's going to do is print out 100 bits of precision. And if you take the bits 2 to the 100th power, it'll come out about 30 digits, and that's about what you have here. Okay, so that's what that means. Now, if you actually want 100 digits, you'd say print pi.n parenthesis digits equals 100, and you actually get 100 digits. And in fact, if you say here's pi to 1,000 digits, I put print pi.n digits equal 1,000, and actually it doesn't take long. It took that much time to generate 1,000 digits of pi. You can put in 10,000. At some point it's going to truncate it. Try putting in 1,000,000 digits, you'll see what happens. It'll take a little longer, but it'll truncate it. It'll give a first big huge block of digits, and then it'll say dot dot dot, and then it'll give the last block of digits, and it leaves out a big chunk out of the middle. So if you exceed the capacity of this thing to simply hold all the information, it'll do something like that. It'll do things like factoring. So if I say factor 1,001, I like 1,001. It's sort of an interesting number. It's 7 times 11 times 13. So the first 3 prime numbers you come to that don't have easy divisibility rules, multiply them together, you get 1,001. Here I just typed in a whole bunch of digits, and I get the factorization. It's pretty impressive. Here, let's do some more. I'm just going to add a bunch of digits in there. Have no idea what its factors are. So notice it has one huge prime factor and then 2 smaller prime factors. So The only things that divide into this of reasonable size are 5 and 79, and then the rest of it is a prime. Okay, let's just change one digit here and see how much that changes it. There's no particular rhyme or reason here. So 5, 7 times 7, or 7 squared, and then two other larger primes that make this up. But it figured that out. It's impressive. Okay. How about the prime numbers up to 100? Well, this is the Eratosthenes, sieve of Eratosthenes method. And so there you go. It does it. How about primes up to 1,000? It does that too. And so forth. All right. No, what you're seeing before I hit evaluate is I evaluated it before, but you're seeing how quickly it reevaluates it just on the spot. Okay, the real purpose of this was to get into matrices. I just wanted to wow you with some of the capabilities of this program. Okay, so if you want to get into it, there are lots of tutorials available. Warning, SAGE is something that operates at the level of high-end math, so PhD level math. However, it's useful all the way down to say high school level math as well. So you just have to pick and choose. And so if you get into the tutorials and the documentation, you'll very easily get over your head. So just back off from those things. Let's say we want to construct a matrix. So this is a 2 by 2 matrix, a square matrix. You only have to put in one digit, and it'll create a matrix of 2 by 2, and there we have it. And it'll be zeros if you just construct it this way. Or a 3 by 3 matrix, there it is. Or if you put in 2 parameters instead of just 1, it'll do a rectangular matrix. This one is 2 by 3. Okay. Now, a list can be made by using square brackets and numbers with commas between them. Okay, so if I create a list, that's a list. Okay, a two-dimensional array of numbers can be thought of as a list of lists, and you can set it up that way. So here's a list with 3 numbers, comma, 3 more numbers, comma, 3 more numbers, and these are actually lists within an overall list. Okay, and so there we have a list of lists. Now, a vector looks a lot like this list of 3 digits here, and a matrix looks a lot like this list of lists, sort of an array of like 3 rows of 3 digits each, okay, 3 numbers each. All right, but in order to make them behave mathematically like vectors and like matrices, we have to actually construct objects that behave in the right way. So if I want to take a list and turn it into a vector, I have to say vector parentheses, notice the rounded parentheses, and inside of that I'm going to put a list. So you have vector, rounded parentheses, and then square brackets to enclose your list, and then you end with rounded parentheses. And what that does is it produces something that is printed as with rounded parentheses 1, 2, 3, but it's an object which internally it knows it's supposed to behave like a vector. Okay. Similarly, if you take a list of lists, which looks sort of like a matrix, you can actually make it behave mathematically like a matrix if you use the matrix constructor. Notice matrix with rounded parentheses surrounding my list of lists. So you get this sort of weird construction here. So I use rounded parentheses and then square bracket, square bracket. The outer square brackets encloses the list, and the inner square brackets enclose the lists that are within the larger list. Okay, the rounded parentheses are what are associated with this matrix function. Okay, so if I create a matrix out of this list of lists, it will create something that's displayed like this, but it'll actually function as a matrix. And here I just commented some more about that, what I just now mentioned verbally. Okay. Now, what if you want to create special matrices? There's a number of them, and one in particular that you should know about is the identity matrix. And there's a special constructor for that, just identity underscore matrix 3 will give a 3 by 3 identity matrix. An identity matrix has a diagonal of 1s and 0 everywhere else. If you said identity matrix 2, it would give a 2 by 2 identity matrix, and so forth. Okay. Now, here are we're just constructing some matrices and vectors here because we're going to use these in what follows. So I'm printing A, B, I. There's A, there's B, and the identity matrix I. And notice that these match the data as they were input up here. Okay. And then I put in actually 2 vectors, but the second vector I put it in 2 different forms. Here's vector V, here's vector W. And notice that if I take 5, 2, 9 and just enter 5, 2, and 9, Sage will tend to treat these as integers. But if I put 5.0, which is what I do up here, 2.0 and 9.0, I'm telling Sage I want to treat these as real numbers. And so it'll give decimal approximations that are not very approximate. They're very precise decimal versions of the number. Okay. Okay, dot products of vectors. If I take the 2 vectors here, v and w, that I defined up here in this statement. Notice, by the way, when I defined something earlier in this series of cells, those stay in memory and can be used later on in further cells down the row. Okay, print v star w. The star acts like a dot product when you're dealing with 2 vectors. If these were just ordinary numbers, the star would indicate multiplication. So the dot product of v and w is defined as, here's v and here's w. I would multiply the corresponding elements and then add them up. So here's 63 plus 10 plus 15. So 63 and 10 is 73, and 15, that's 83, and 5 is 88. There you are, 88. So if I evaluate that again, it comes out 88. All right, a matrix transformation of a vector. If I take a matrix times a vector, it will come up with a vector. That's the way you can take a matrix and make it act like a transformation. If I apply that to a whole series of vectors, it'll transform the input series of vectors to an output series of vectors, which might do something like expand or rotate or shift this pattern of vectors that you input. If you multiply 2 matrices, that's like compounding 2 transformations. You can use matrix multiplication. So if I go A star B, I get this. If I go B star A, I get a different matrix. Just to point out the simple counterexample here, matrix multiplication is not commutative. So you have to be careful whether you're doing a left multiply or a right multiply whenever you say you're multiplying a matrix by something else. Okay, and there it is. I reevaluated it. Okay, now the identity matrix, which I defined above and called it I, has the diagonal of 1s. If you multiply that on either side, it's going to leave the matrix unchanged. So here's A itself. Here, let's evaluate it. This is A. Here's A star I. That's this one, which is identical. And here's I star A, which again is identical. Okay. Okay. This says multiplication of matrices or matrices and vectors is, however, associative. And that's very important. We're going to see, I have a comment on that here. So consider if I have 2 transformations that I'm going to apply to this vector. So A and B are matrices and V is a vector. If I take A star B and do that first, it takes these 2 matrices and makes a single matrix out of it. Then it takes that matrix and operates on the vector V. Over here, what I've done is I've taken my vector V and I'm taking B star V. So I'm doing a transformation of V, which will produce another vector. Then I take A star that vector, and that's going to give the resulting vector. Well, notice if I do it both ways, I'm going to do this form here in this form here, and I have a couple of lines in between. Notice I get the same result. Multiplication of matrices and vectors and so forth is associative. So it doesn't matter how you group them. It does matter how you arrange them. You can't just interchange the A and the B as we saw above, but you can group them any way you like. Now that's very important. I did a program back in the 1980s and 90s that did astronomy, and I think the database is like 200,000 stars or so. And there are times when I'd want to rotate the whole dome of stars to put it in a different coordinate system, for instance. And the way I accomplished that is I did a series of transformations. And so say that I do this one that says, what if you apply a sequence of 5 transformations to all the stars in the database? So each star is represented by a vector. Okay, so you have A times B times C times D times E times your vector. Well, you could take your vector and apply each of these 5 transformations in sequence to it. However, the other way to do it is to multiply these 5 matrices together. That's only 4 matrix multiplications. What you get is a single matrix. Then I take that one matrix and multiply it by all 100,000 stars, all 100,000 vectors. So instead of doing 100,000 times 5, giving me 500,000 matrix to vector multiplications, I do one combination of the 5 matrices, and then I take that single matrix and multiply it by 100,000 stars. So I end up doing 100,000 instead of 500,000 matrix multiplies. Okay, so that's just an illustration of how the associative law is so critical in actual applications. Okay, there's nothing to evaluate here. Okay, matrix inverses. In ordinary multiplication, an inverse is the same as a reciprocal. And so if I wanted to take, say, 2 times its reciprocal, which is a half, notice that 2 times a half comes out the identity, which is 1. 5 times a fifth comes out the identity, which is 1. So that's the nature of what's known as an inverse. If I take a number times its inverse under multiplication, then I get the identity, which is 1. If I take a number added to its inverse under addition, like 2 and minus 2, 5 and minus 5, I get 0, which is the identity under addition. Well, if you have the identity matrix, which is this matrix with a diagonal of 1s, and if I multiply a matrix times its inverse matrix, it would come out with the identity matrix. Okay. Now, the way we write inverse of a number is we would say a to the minus 1, and the way you'd actually write an inverse matrix on paper is say a to the minus 1, indicating a matrix. Okay. You can actually do exactly the same thing, except you have to be a little careful. This means raised to the, like an exponent, but then you have to put parentheses because the minus and the 1 have to both be up in the exponent. Okay. So if you write it that way, it'll actually produce the inverse matrix. Okay. So let's like BB as a label equal B raised to the minus 1, or in other words, the inverse matrix is the symbol that's being represented here. This is not actually doing an exponentiation. It's just a symbol that stands for the inverse matrix. So then if I print BB, here is the inverse matrix of the B matrix. Okay. Now the other way to do it, instead of putting all of that symbolism in, is to just use the inverse method. So if you take B dot inverse and put a couple parentheses to indicate that that's a function. Whenever you have a function, you have to put the parentheses whether there's anything in it or not. And so this is sort of like a function that's embedded in this object. And so it's just B dot inverse with parentheses. And that's going to create BB. If we print it, notice we get the same thing here as we did before. And so that's another way of getting an inverse. Okay. Now, let's try. Let's multiply B times BB. We're going to do a matrix multiply of matrix B times its inverse, and let's multiply the inverse times B. So I'll try it both ways. And so here it says print B star BB, and then print BB star B. And I evaluate it, and notice in both cases it comes out the identity matrix. That's the nature of an inverse, is the an element times its inverse gives you an identity. Okay, a singular matrix is one where the determinant is 0. This ends up producing a 0 in the denominator when you're computing the inverse, which could cause problems. Okay, I'm just warning you here, there are some matrices that don't behave like the matrix B did up here. And in particular, the matrix A is singular. If I take the inverse of A, it gives me this error message. It says 0 division error. One of the things about a matrix, take a matrix like any of these, all right? Let's go back up here. Take a matrix like this. In fact, this one is A, all right? It turns out the determinant here is if I think of these three vectors, the three rows as separate vectors. And if I think of those three vectors all starting at the same point and reaching out in space, and then complete sort of a parallelogram in 3 dimensions. It's called a parallelepiped, sort of a parallelogram, distorted kind of a rectangle, a rectangular solid or a box. All right, sort of a slanted up box or something. If you take the determinant of a 3 by 3 matrix, it will give you the volume of that parallelepiped. One possibility, though, is that these three vectors don't span 3 dimensions. They all lie in one plane, so that one of the vectors could be expressed as some kind of a combination of the other two. Then the volume of this thing is 0. And so if you have a matrix whose determinant is 0, it's a clue that this thing collapses down. It doesn't really completely occupy 3 dimensions. It's actually a flat thing embedded in 3-dimensional space. And when that happens, trying to invert it, trying to go back the other direction, you can't recover the lost dimension. You've lost information in the process of crunching something down to one less dimension. Okay, so that's essentially what's behind this problem. So if you have a matrix which is singular, whose determinant is 0, it's a matrix that collapses a 3-dimensional, for instance, space down to 2 or 1 dimensions. Okay, and so that's a case where you can't work with it. So if it's a singular matrix such as A, you try to do the inverse, it gives you this error message. There it is. There's the error message. Okay. If you're interested to find out whether a matrix is going to give you that kind of problem, rather than trying it out first, you could find the determinant of the matrix. And so if I take the determinant of A, notice it comes out 0. The determinant of B, on the other hand, comes out a non-zero number. It doesn't really matter here what it is. It's negative 209. Okay. Okay. Next application. Consider a system of equations, and here I took 3 equations and 3 unknowns. We could just as well have taken any number of equations and the same number of unknowns. So here's x, y, z, and a constant on the other side. All right. Notice that you can represent this left-hand side of this system of equations as a matrix dotted with a column vector of x, y, and z. So if I took x, y, and z and multiply it across the top, it would be x times 1, y times 4, z times 9, and add it up. And that's exactly what this first equation says. And then you take this across the second row, and you get that, and this across the third row, and you get that. This is simply a symbolic way of writing a system of equations as a matrix times a vector, which then is equal to this constant vector on the right. Okay. Well, this becomes a matrix equation. How do you solve a matrix equation. Well, how would you solve this if it was just a numerical equation? Here's your variable, and here's a number, and here's a number. Well, I would take the inverse of this number. If this were 2, I would multiply it by a half on both sides. Now here we have to be careful because it matters whether we multiply on the left or multiply on the right. So I'm going to left multiply the left-hand side by the inverse of this matrix. That'll turn it into an identity matrix, which just means it will cancel it out. So if I take that same inverted matrix and left multiply it on the right-hand side, what I'll get is that xyz is equal to that inverted matrix times the 529. So how do we figure out x, y, and z? I take the inverse matrix times this constant matrix. Okay, so let's try it. Let's solve a system of equations. Notice this particular equation that I laid out here. This is the matrix I've labeled as B, and this is the column vector here that I've labeled as W. All right, so if I simply take the inverse of B times W and then print it out, notice I get 3 numbers. And notice, by the way, how Sage computes these as fractions. It'll do that if it can. All right. By the way, notice how I use this pretty awkward inverse notation. Let's change it right here. Let's say dot inverse parentheses, open and close parentheses. So that does the inverse matrix times W, and same result. Okay. Now, let's try it again, this time using Z instead of W. Remember that I defined Z exactly the same as W, except I put decimals in there, which told it that I want to use real numbers instead of rational numbers or integers. Okay, and so if I do this, let's again change this to the other notation. I actually like that other notation better. So B dot inverse times Z, and sure enough, it comes out. This is the same numbers as these. If you take out a calculator and take 35 over 19, you will get this, and so forth. All right. Well, how do you test the results? Well, let's go back up and look at this. If I take my results, that's this xyz vector. Okay, so that's the calculation we had here. So if I take my original B times my result vector, it should give me 529. Let's see what happens. Okay, so print B times the first solutions. The first solutions were using the rational numbers, and then I have space, and then I have B times the second solutions. Those were using the decimal numbers. Okay, in the first case I get 529. The second case I get 529, except in a different form. Okay. All right. So I'm just commenting here that Sage will try to work with rational numbers unless you tell it explicitly. In fact, you can with matrices. There's parameters you can put in there. It will tell it whether you're dealing with real numbers, rational numbers, integers, complex numbers, the different things you can apply. Okay. Okay. Using inverse matrices will not work if the coefficient matrix is singular. We saw that you can't take the inverse for matrix A because it's singular. And if I try to solve the equations with A instead of B in there, it gives me this error message which says you are dividing by 0. Okay. So that sort of winds up this little introduction. I also want to point out that using matrix inverses is computationally kind of an intensive process. I haven't gone through how you compute the inverses here, but if you do it by hand, you'll realize you don't want to do it by hand every time. So typically, matrix inverses, you'd want to have some kind of machine working with you. So either a computer or a high-end scientific calculator, something that will compute inverse matrices for you. Then you can just use them and take them for granted. They are very significant theoretically when you're trying to do when you're trying to study the algebra of matrices and vectors and so forth. So yes, they're not something to ignore. There are probably computationally somewhat simpler ways to approach these same problems, but matrix inverses in general, just like multiplication inverses and addition inverses, are part of what makes up the algebra of these different systems. So there we go. Sage is a tool to be used, and so go for it. It's a very powerful calculator. Think of it that way. Is it okay to use this with schoolwork? Well, in my schoolwork, you sure can. Other people will take different attitudes, I'm sure, but technology enables you to do problems that you would never even attempt if you didn't have the technology there. So I think it's good to expose yourself to real-world problems that might have messy answers and things like that. So yes, use calculators, use computers, use whatever you have accessible, not to replace learning, but to empower you to solve bigger and more real-world looking problems.